Welcome to existence of the Laplace transform. So recall again the Laplace transform. Of f of t is defined by Laplace transform of f of t, which equals f of s, which is the improper integral from 0 to infinity of e to the negative s times t times f of t dt. This Laplace transform may the Laplace transform does not have to exist for any s. Or it may exist over a sort of standard domain. So the question becomes sort of, are there conditions that guarantee the existence of a Laplace transform somewhere? And so that's what this will be getting into here. So definition, function f is piecewise continuous on the closed interval from 0 to capital T if the following are true. First up, the limits at the ends exist. So the limit as t approaches 0 from the right of f of t exists. And the limit as t approaches capital T from the left of f of t exists. Next up, f is continuous on 0t except at a finite number of points. Which we will call t sub I. And then last up, each of those t sub i's, so for each t sub I, the limit as t approaches t sub I of f of t exists. The limit as it approaches from the left exists, and the limit as t approaches t sub I from the right of f of t exists. Just a little comment here, when I say these limits exist, I'm referring to the limit being finite. So the limit exists. I'm using the fact that the limit is finite. So the limit is equal to some L, which is finite. So essentially what we have here is we have a function which is continuous and except at some finite number of points, and And at those finite number of points, it has to be heading in to approach a specific point. It's not going off to infinity, and it's not oscillating faster and faster and faster. So it's got sort of controlled bounded behavior. So this is piecewise continuous on a closed interval from 0 to t. Next, we're going to do piecewise continuous from 0 to infinity. So a function f is piecewise continuous on the interval from 0 to infinity if f is piecewise continuous on the closed interval from 0 to capital T for all t greater than 0. So piecewise continuous on 0 to infinity does allow us to have infinitely many breaking points, but those breaking points have to be spaced out enough that there are only finitely many on any smaller interval. So essentially, for piecewise continuous, we have a bunch of pieces. You can have what are called jump discontinuities, or you have a break, or we can just have a removable discontinuity, a hole. But this is sort of piecewise continuous. Essentially, it's bounded. It's not going off to infinity, and we don't have these crazy infinitely many oscillations going on in a condensed space. Next definition, another thing that will be useful, is a function f is of exponential order S naught if it is bounded, or if it is eventually bounded by an exponential function by which I mean so that there exist constants m and t naught such that the absolute value of f of t is less than or equal to capital M times e to the s naught t for all t greater than t naught. So in this case, we have our exponential function, which is bounding. It can be either growth or decay. Let me update my screen. Here it's bounded both above and below. And it only has to be true after some t naught. So anything can happen before that point. But after that point, it has to stay within the bounds. Right? So it stays within the bounds after t naught. So we have negative m times e to the s naught t is less than or equal to f of t is less than or equal to m times e to the s naught t for t greater than t naught. So this is what we mean. It's exponentially bounded, or sorry, it's of exponential order s naught. So we get a theorem which tells us that if f is both piecewise continuous on the interval from 0 to infinity and of exponential order s naught, then the Laplace transform exists. So the Laplace transform of f exists for s greater than s naught. So a very rough version of this proof. So this proof sketch. Right. If we want to take the Laplace transform of f, this is the improper integral from 0 to infinity of e to the negative st times f of t dt. And this should be equal to the integral from 0 to t naught of e to the negative st times f of t dt, plus the integral from t naught to infinity of e to the negative st times f of t dt. Now, this first one, we are taking a proper integral of a piecewise continuous function. So f of t is piecewise continuous. So we should have e to the negative st times f of t is piecewise continuous. And specifically, both of these are piecewise continuous on the interval from 0 to t naught, since they're on piecewise continuous on the entire interval from 0 to infinity. So e to the negative st times f of t is piecewise continuous on the interval from 0 to t naught. So we have a bounded function. And we have continuous with any limits we do have are finite. So e to the negative st times f of t is bounded on 0 t naught. And so we know that the integral, definite integral from 0 to t naught of e to the negative st times f of t dt exists. So that's that first integral. The second piece since f is of exponential order at s naught, we have And with absolute value of ft less than or equal to capital M e to the s naught t for t greater than t naught. So the t naught I picked earlier is this t naught. Then we have that the integral from t naught to infinity of e to the negative st times f of t dt should be less than or equal to the integral from t naught to infinity of e to the negative st times the absolute value of f of t dt, which is less than or equal to the definite integral from t naught to infinity of e to the negative st times m e to the s naught t dt. We can rewrite this. I'm going to keep writing less than or equal to's, but these are technically equalities at this point. Pulling out the m, we have the definite integral from t naught to infinity of e to the negative s minus s naught in parentheses times t dt. This integral exists as long as s is greater than s naught. So therefore, the original Laplace transform exists for s greater than s naught. So this is sort of where this theorem comes from. Again, this is not a fully extensively written out proof, but it's kind of the idea. Just a quick note. These conditions are not required to have the Laplace transform exist. But they do guarantee existence of the Laplace transform. I apologize, I regularly misspell guarantee. I don't know how it's spelled. So if we can show that a function is piecewise continuous on 0 to infinity and that it is of exponential order s naught, then we can guarantee that the Laplace transform exists for s greater than s naught. Just because those conditions are not met does not mean that we cannot, that the Laplace transform does not exist.